because it's the. Welcome everybody. This is STLE Toronto, STLE Hamilton, first joint meeting like this ever. But thank you to Bill Quesnel and the WearCheck team here. We also kind of combine the lab tour with the presentation. We also have to mention before we start our sponsors, which in this case, very close home, I guess, Petro Canada and WearCheck. Thank you for the help, Bill. The presentation today, after, well, hopefully you guys enjoyed the food and enjoyed the lab tour and probably have a lot of questions as well. Some of those questions, if they haven't been answered at the end of the day, it's Paul Dumont here as well, and Bill and Gloria, so stick around and ask any questions. It's no new to us being in WearCheck, talking about from the STLE, Toronto or Hamilton. A lot of people, familiar faces, but I would say take some time, get to know the person that is beside you, the person that is, probably is a little shy to talk. Networking is important. It can help us to actually make more sense of these meetings. So that being said, we got a couple of titles before. I think that we nailed the best title to actually get this recorded. We call it Ghost Particles. Still, they're going to be talking, Bill is going to be talking a lot about ISO methods and so on, but that's a nice title, I believe, attract people. So just a quick introduction. Well, first, I think Bill doesn't need the introduction, but well, he's the president of WearCheck Canada, and we are in his house today. Thank you, Bill, again. He got so many different certifications that I don't want to mention. But yeah, he's gonna be probably, I would say, talking for a little bit before and after this presentation, right? So we got, I would say, was a kind of a joint forces here, trying to talk a little bit about these ghost particles. You're gonna know a little more about it. And that's why you see also some familiar faces probably from some of the Petro Canada folks. Sonia Evia, which is our R&D specialist that contributed to a case study that we're gonna be talking about it. And then we also have one of the partners of WearCheck, I guess, Alistair Gish. He's not here, right? Oh, he is. He is? Someone, okay. All right, okay, awesome. So, well, that being said, I'm going to give you Bill, and thank you again for all the help, and enjoy. I think that we have a good crowd. How many we have there on the call? 9. I think that it's the first time that we beat the virtual people. So we are around 30 people here, or 25? Okay, awesome. Thank you, Bill. Go ahead.
Thanks. All right, well, thanks very much. I don't think it was the ghost particles. I think it's the tacos that brought everybody in. So, but I think that's a great title for a paper, and it was Sonia actually. You want to roll back to the first slide there? So it was Sonia that came up with this. She sent me some slides and she said, could you please incorporate these into your presentation? Ghost particles, my little ghost. That was my first try at generative AI. It's now in Photoshop. So that's what a ghost particle looks like, apparently. But yeah, we want to talk tonight about the impact of these particles in ISO cleanliness codes. So we're going to give a little bit of background and history on what we're doing for ISO cleanliness and talk about what some of the issues facing us today in the industry and people out there who are trying to interpret their oil analysis results and why this is an issue. So as Yen mentioned, so just quickly to go over, so Synergy Systems is another company that we have here, and we develop instrumentation that we sell to laboratories around the world. So our competitors in the oil analysis world are our customers in the instrumentation world. And really the reason we did that is that we recognize a number of pinch points in oil analysis laboratories. And the first one was particle counting, what we're going to be talking about tonight. So particle count testing As you know, there's been more and more emphasis on cleanliness of oils, especially with companies like Noria out there doing a lot of education and training, and now everyone's on the bandwagon. We all talk about cleaner oil means longer equipment life. So our laboratories were filling up with these tests, so we developed automated instrumentation for doing particle counts. And we did this because there's a new method out that allows for dilution of oils prior to doing particle counting, and that's going to be a big focus on how we deal with these ghost particles and how we're going to talk about this tonight. So Alistair is my CTO of Synergy Systems, and he is around here somewhere tonight if we want to go over and talk to him and see some of these instruments over there. And Sonia, of course, has been a research chemist at Petro-Canada for over 16 years, has a PhD in nuclear analytical chemistry, so a very bright lady. And she sent me some slides, which is very interesting because it's a study that we've been doing at Synergy as well that we'll be presenting in Spain and probably then later in Germany and in Michigan as well at Lube Expo. So something we want to talk about. So it fit very well for tonight. So what? What are we going to talk about? The big emphasis here is that there's an issue with a lot of particle count results going out to today, and they become very critical for people who are trying to use filtration to clean their machines and keep their oils clean and get longer equipment life and more reliability, because there are a number of non-abrasive particles that are present in oils that cause increases in the inherent particle counts that show up on your reports. And these are insoluble oxidative byproducts. So as oil degrades and produces products that are insoluble in the oil, these have an effect on particle count. And in some cases, additives. So I think a lot of people are aware in our industry now about the effects of water and insoluble oxidative byproducts and particle counts, but they're not aware so much about additives playing a role. So that's one of the things we wanted to study. And how do they do this? Well, those particles cause light scattering inside optical particle counters that are out there today, and we'll have a little look at that. And so they create these erroneously high counts that people then take maintenance action based on. So they're wasting money. And in fact, we'll see where it can actually cause other issues as a result of it. And it comes down to the fact that these optical particle analyzers can't distinguish between these phantom ghost particles, these soft particles, and abrasive particles, what we really should be measuring with particle counting methods. So we're going to talk a bit about a dilution method that's used, but even that didn't solve the problem entirely because of some of the solvents that are used for the methods. We want to discuss that. So as I was mentioning, filtration has become everything today in oil analysis. We didn't do many particle counts decades ago, but today it seems that vast majority of the samples we test in here get a particle count for ISO cleanliness code. People are doing filtration on just about everything out there, from permanently mounted filtration systems to offline filtration, vacuum dehydrators. I mean, it's a huge industry. I know there's some people in here tonight who are selling filtration as part of their business. We've seen through the likes of Reliable Plant and SKF and the Oklahoma State University that there's a number of tables out there that show if we get cleaner ISO cleanliness codes in our oil, if we're taking the dirt and particulate out of our oil, that we can get increased equipment life or mean time between failure increases. Same with water levels. You put those two things together, if you can keep your oil cleaner and drier, you can get life extensions, depending on the type of critical components in there, anywhere from a 10 or 20% increase to 1,200, 1,300% life increase in equipment. So, and we all know that this is what we want to achieve today. And a lot of people are using oil analysis to validate that the filtration improvements they're making on their components and equipment and in their oil storage and in their oil handling is having an impact on the reliability of their equipment. Warita time. So how do we measure oil cleanliness? So we have an instrument that will measure the amount of particles that are in an oil and hopefully just those solid abrasive particles. We measure them at 3 distinct sizes, and I'll explain that in a minute, but just bear with me. We measure them at greater than 4, greater than 6, and greater than 14 microns. And we measure the amount of those particles in those different size ranges, and then we convert those from an actual value to an equivalent classification scale on ISO 4040-06 table. So we take those amount of particles and find the scale that corresponds and get that number, and we report that as 21/19/13 as our cleanliness code. The 4, 6, and 14 is really kind of an artifact of the fact that many years ago, when we were first running particle counting tests and using particle count instrumentations, whether they were online or on site or in laboratories, we were looking at only the 5 and the 15 micron particles. So people who have been in the industry longer recall that there used to just be a 2-tier code. It would have just been a 1913. And it made sense. It was 5 and 15 microns. Those sound reasonable. 5 was representing particles that were more silt-like, smaller, that would cause stiction, those sorts of problems in servos and valves, spools. Whereas those greater than 15 micron particles are usually indicative of something like seal failure or wear particles, gross contamination. But along the way, when the particle counting became more prolific and people wanted to tie that back to better analysis and better quality of results, we had to tie the calibration of these instruments back to primary standards. We had to come up with a primary standard. The original standard for this was called AC Fine Test Dust because it was made by AC Delco, and it was dirt out of the Phoenix Desert. So apparently they ran out of dirt. So we had to come up with something different. And at that time, that wasn't a traceable standard. It was an amount of dirt put into oil. So you couldn't create what you call a primary standard for the type of calibration that people do in laboratories. So they came up with something called MTD, or medium test dust, that's now put into a super clean fluid and produces a particular standard that's now used in our industry. And when they did that, the ISO numbers changed. The 15 came down slightly and the 5 went up slightly. And what it did is everybody had these ISO cleanliness targets in their manuals for their hardware or their hydraulic pump, and suddenly those values didn't coincide anymore. So there would have been outrage. So what they had to do was take the 5 micron and make it a little smaller, a 4 micron, and they took the 15 and made it a little bit bigger, 16, and that brought those numbers in line. And so nobody complained. Yet I have to stand here now and explain that to people because 4, 6, and 14 don't make sense. And of course, they added in that smaller number. When we first started doing it, when it was 5 and 15, they put a 2 micron in, but eventually that sort of settled out as a 4 micron. And it turns out that the very small particles in a lot of these systems are the most critical. And these are the particles, as I mentioned, that really cause problems with valves and spools and the very sensitive components that exist in turbines and hydraulic systems and circulating systems today. So there's a variety of different instruments used for doing particle counting. We have flow decay type particle counters that were very prevalent on site. It's a completely different methodology from what's used in laboratories today. Optical is kind of the standard. There's inline optical. Some people have them installed right on their filter carts. And with PLCs installed, you can actually hook it up to a piece of machinery and run the oil through it and hit a certain cleanliness code and shut the cart off automatically. Or they can be synced up with IoT devices and hubs, and then we can be taking continuous readings of the ISO cleanliness of our oil. On-site particle counters are also very common in a lot of different plant and industrial environments. And then we get into laboratory style. The older hygroid syringe driven, and this is one of the type of instruments we manufacture now. So because there's been such a demand for particle counting out there in our industry, there are much larger, fully automated systems available for doing particle counts in laboratories. So the test itself, whatever instrumentation you're doing, as I say, you're taking a representative, hopefully, sample of oil, and that is beyond the scope of this presentation today. But Paul was running a Loop Hero course today, and one of those sections is purely on taking representative oil samples from machinery and equipment and oils in storage. But hopefully you're taking a representative sample of your oil. you're doing your own particle counting on tests with your own portable instrument, or you're sending it into a laboratory, and we're doing the particle count for you. But we are measuring the amount of particles in a milliliter of oil at those different size ranges, at least 4, 6, and 14 microns. Usually there's a number of other size ranges which are just as ambiguous as these today, 21, 38, and 70, which used to make more sense. And ultimately, we're producing that cleanliness code, ISO 4406, which gives you that 3-tier ISO code. And the lower, the better. The one significant thing about these codes, you can see on my chart here. So I've got the ISO cleanliness code running up the right side, and I've got the number of particles. You'll notice that this is not linear. This is a factor of 10 every time we go up, because every time we increase one number on this, we're doubling the amount of particulate. So if you go up 3 ISO codes, that's 8 times as much dirt, 4, 16, et cetera, et cetera. So a 4-level increase is quite a dramatic increase in the amount of particulate you're actually seeing in a sample. How do particle counters work? So optical particle counters today use a laser sensor, which is the source. And we have it pushing the oil through some type of a tubing or piping through the actual detector where the laser is. And essentially the particle itself comes into view and occludes a portion of the laser light. And that is measured as a voltage pulse, both time and voltage, which gives you an indication of the size of that particle. So imagine that happening thousands and thousands of times per second, and that's converted into through an analog digital converter to an actual particle size data, so we can record those amount of counts. Obviously, we're counting a little bit more than a mil of oil. We're counting a volume of oil and then dividing it to get the counts per 1 mil. But that's a pretty standard count of particles in a milliliter of oil. So, that's one of the myths, is that you still see that where people will take a sample out and say, oh, it's nice, it's clean, right? But I mean, those particles, all those particles there are not even visible by the human eye. The problem with optical particle counters, which are on-site labs, built-in online sensors built into filter cards in most commercial labs around the world, is that they have a inherent problem with what we call soft particles, as well as water. And what that does is, when those particles come through the detector, unlike a solid particle, which we want to measure, they tend to scatter the light. And that scattering has a dramatic effect on the amount of perceived particles in there, and more on the 4 and the 6 micron. Use my pen. So most dramatically, the 4 and the 6 micron increase. So this is the real issue. So anything, and soft particles, we refer to things like insoluble oxidative byproducts, which are varnish precursors. Those are the things that are going to eventually drop out of the oil and form these shellacs and varnishes on your components, sticky, and then eventually become really hard solid resins, and then interfere with the ability of the oil to dissipate heat, eventually cause stiction in turbines. It's the major reason for an outage. So the turbine EHC systems will trip if there's too much insolubles in there. So we do want to know something about that, but we have tests for doing this. So we'll see a couple later. But really, we're just, in this case, we don't want to be counting these. We just want to be counting solid particulate, because ISO cleanliness codes are all to do with abrasive particles. So a number of years ago, a new ASTM method came out. And it's interesting. I did a presentation to the Hamilton STLA section. It was probably about 15 years ago, and they said, I want you to come talk about new oil analysis methods. So I was like, great, no problem. And about a month later, I'm like, there are none. I looked through every ASTM book. I think I had like 2 or 3 new methods to talk about. We were back in the ASTM 3000s then. We're up in the 8000s now. There's been just an explosion of ASTM methods. A lot of them have been very beneficial to our industry. This method has been very beneficial to try and help us make particle counting globally a lot more reproducible and repeatable, meaning that if you send a sample to 4 different labs, you want to kind of get the same number. If you would have tried that experiment 10 years ago, even, you can get any number you want. So, and in fact, some people would. Let's just send it to 4 labs and we'll just take the lowest number. That's the one I want. But part of the problems with that was the fact that these soft particles in water were causing a lot of interference, a lot of differences in particle counts. So this dilution method came. Is that 5 different diluents or solvents that are allowable, and a lot of them have very different properties in terms of being effective masking agents for soft particles and for water. So that's what we wanted to study. If you use the right solvent, the potential is you can easily mask up to 2% water in an oil with just a simple 1-to-1 dilution. You can mask the effect that's brought on by additives like antifoamants, anti-friction wear modifiers, and antioxidative byproducts, color bodies, varnish precursors as well. So the solvents that were studied in this were toluene IPA, so IPA is isopropyl alcohol, and what it does is if you mix it in with oil that has water, it takes the water and it forms an azeotrope. I tried to find a nice picture of that. There are no pictures of that. There's graphs, but no pictures. But essentially, it masks the water. And you'll see in a second what I'm talking about. The toluene itself is a really good solvent, so it resolubilizes anything that's not solubilized in the oil, like insolubles. Ethylene glycol butyl ether. This is a good agent for masking water. Also has good solvency. Dowinol, which is a Dow product that is very similar to EGBE. Kerosene, which is a really poor solvent, but nonetheless is part of this method and allowed for dilution and has absolutely no masking properties for water. Varsol or Stoddard solvent, identical to kerosene, also not very good. And then we looked at a mixture of kerosene with some Dowinol, which does have some pretty good properties for masking water and improving the solvency of the oil. So just in terms of insolubles, because I want to focus on additives, but it's worth noting that one of the biggest problem we see is that when we're looking at hydraulic oils or turbine oils, circulating oils, that if we leave those oils in there for appreciable amount of time, we eventually have those oils degrade to a point where it's forming a lot of insoluble byproducts in there. And what that means is every oil has a certain level of solvency. And we were having a conversation about API group 1 and 1 plus, which is a new one for me in the last month. I've heard that twice now. But and there's group 2 mineral oils and group 2 plus and group 3. So all those mineral oils have certain levels of solvency, and I think we can all agree that the API group 1 is known for having better solvency than group 3 product. And then we have group 4, which are polyalpha olefins, what in the olden times we used to call synthetic, although group 3 is now considered synthetic today, right? But PAO-based oils have very good applications, very good oxidative thermal stability. The problem is they have very low solvency. So you can't really additize them much, and they don't really like varnish, and they produce insolubles much quicker. And then group 5, which is every other kind of oil out there, whether it's polyesters or diesters or polyalkylene glycols or silicone-based oils or fluorinated oils. So oils have different levels of solvency. Eventually, though, they do get insolubles in them. And when we take a sample of an oil that has a high level of thermal degradation and oxidative degradation, and it has a lot of insoluble products, there's in that oil, and the best description I can think of and I've heard is like a sponge. Think of a sponge. They can absorb only so much, and eventually it's going to come out. And the hotter that sponge is, the more it can absorb. So when you're running your oils up at temperature, and if they're running hot, they have a lot more solvency. They get super saturated with insolubles. You send them to the lab, and eventually all those materials kind of settle out. We increase that by putting that through a very small micron rated patch, actually 0.45 microns. And that's small enough that it captures those, what they call color bodies in the oil. and they deposit on a patch, and we use a small little ultraviolet spectrometer to take a measurement of that and give you a value. In this case, it's 159, which if you know anything about membrane patch colorimetry or varnish testing, that's a very high number. But I wanted to use that as an example. So typical oil in use might be 15, so that's 10 times that level. But when we mix that oil now, that oil sample 1-to-1 with one of these solvents, so if we do toluene and we put that out on a patch, you can see there's a bit of insoluble deposits there. You can see the particulate as well. And a particle counter diluted with toluene is going to see that as a 171511 cleanliness code. But if we put that through with kerosene, then you can see the actual deposits are soft particles. And the particle counter says that it's a 232321. That's a significant difference. So as I mentioned, the 4 and the 6 are dramatically affected in undiluted samples compared to diluted. And the solvent has a major effect on that. So we took a stressed oil that had been in service. This is a mobile DTE 846 in a turbine, probably a steam turbine system. And it had a fairly high membrane patch colorimetry test or varnish test, a delta E of 60, which is, it's critical enough that some action has to be taken, electrostatic filtration or some type of a sieve filtration to try and clean the oil or complete oil change and flush. The problem is when you count that with a particle counter undiluted, it's seeing all that color bodies as particles and getting a very high measurement, as we saw, 2319. If we use the butylglycol or Dalinol or the toluene IPA, you'll see that that count comes down dramatically, more back to what it actually is, just in terms of abrasive particles. I mean, we're talking a difference of 9 ISO codes. So who can do that quick? What's 2 to the 9th degree, right? It's a lot. So it's a lot dirtier. The problem was kerosene and Varsol were even worse than the undiluted sample. They were actually causing the insolubles to agglomerate and form larger particles. So you can even see the 14 micron was dramatically affected as well. So sufficient to say that even with insolubles, solvents make a huge difference, whatever solvent you're using in the method. Even at low levels, so even at an MPC of 15, which is pretty standard for an oil in use, we don't see as dramatic of an effect. So again, with those different solvents and even undiluted, it's not bad. So with lower levels of insolubles, particle counts are pretty reasonable. But we go up just a few numbers on that, and there's a huge effect now on those particle counts, whether it's undiluted or whether we're using something like Varsol or kerosene opposed to toluene. You know, and you can do the particle filter and see immediately that the cleanliness code is more a match with this patch than what the undiluted count is saying. Water too. So water contamination particle counts. So here's the sample we received. Had it's emulsifying type oil, so there's 0.35% water, but it's completely opaque. This oil has 14.5% water in it. Again, it just looks milky. But if we use a dilution with a masking solvent like toluene and isopropyl alcohol, this is what the oil looks like after you mix them. So it goes clear, and that clearness is what that particle counter wants to see. If your oil looks hazy or is opaque, then you're going to get these effects. And even a 1-to-1 dilution of the solvent with the oil will mask up to 2% water. So after that, you have to use higher dilution levels. But so we took some of that new fancy calibration fluid, medium test dust, and we spiked it with water at 1 and 2%. And then we tested those various solvents that are in the method. And what we found, of course, is that the butylglycol ether and the Dalinol and the toluene IPA, as expected, do have masking properties. They do mask the water, and we get the actual count we should be getting. But kerosene and Varsol, even kerosene mixed with a bit of Dalinol, even if we don't have enough IPA, which is masking the water, we can see that we're getting very high particle counts. So solvent selection there was critical. This is something we didn't know. I've seen articles on this, but not a lot of research. And that is oil additives and particle counts. And when we first introduced this synergy instrument we have that we use the dilution method with, and we use toluene and IPA because we find it's the best solvent. We had, usually it's the OEM. So you have an OEM manufacturer and they're buying oil from a supplier. In this case, it's Petro-Canada. They get the oil on site. They send it off to a lab tests it and says, this oil is really dirty. The company goes, oh, well, we'll filter it. They filter it, send it back. It's still dirty. Okay. Then they phone you, Petro-Canada, then they complain. You're sending me dirty oil, clean it. So whether you clean it or contract someone or buy them a filtration system, still dirty. Then they send us a sample and we run it with our dilution method and it's clean. I'm like, well, how can that be different? Well, it's different because in this case, we suspected it was anti-foaming agent that because additives in oils, I mean, there's always this sort of dilemma. Can you filter out additives? You know, if we go really small, if we go like to 1 micron, half a micron, are we filtering out the additives? Most additives are on the angstrom level, right? They're infinite, quite a bit smaller than the micron level. But anti-foaming agents tend to be fairly large. These are silicone oils, and they're large molecular chains. So there is a potential. Things like friction modifiers, again, like glycerol monoolate, is also a very large molecular chain. Maybe. We also suspect that they have an effect on particle counts. So one of those products that we looked at was Petro-Canada's ATF D3M, which is an automatic transmission fluid that contains both anti-foaming and a significant treat of anti-foam as well as friction modifier. And certainly undiluted versus diluted, there's cause for concern. But this was some work done by Sonia, and I don't think this has been done to this date. So what she did is she said, fine, we're having a problem with ATF D3M. Let's break this down, as only PhDs in nuclear analytical chemistry do. So she looked at particle counts of the base oil. She looked at a particle count of just with the friction modifier in the base oil, then with the friction modifier plus the anti-foam, and on and on and on. But I think pretty conclusively, she was proving that there's definitely an effect with the anti-foam. I would even say that there's an effect with friction modifier because there's certain products out there that we've tested here where customers were having problems with. A large off-road construction OEM who's bringing in a TDH type product that's a combined hydraulic transmission, drivetrain oil, and has a lot of friction modifier. And they were getting very high counts from their laboratory, but once we brought it in here and tested it with the dilution method, those counts all vanished and the oil was clean as we expected it to be on delivery. So certainly, at least anti-foam is playing a part. I would also say that the friction modifiers is playing a part as well here.
Sir, worked on just a straight base oil.
We didn't, but we'll see some effects here in a second with that, because base oil plays a part as well. So in this case, we're talking likely, I'm assuming this is group 2 base oil, but obviously undiluted, we're getting very high particle counts on this product, and this is what started this whole issue with this particular OEM. But we can see that if we use a toluene IPA as a solvent and do the particle count drops by 6 codes. So it's quite dramatic. And we back this up by doing particle debris patches, and the patches are clean. The interesting thing with this, though, is that the butyl glycol and the Dawanol didn't seem to have that same effect. In fact, they were causing an issue in some cases. Was not what we noticed with insolubles, not what we noticed with water. They seem to be effective there, but they're not effective at masking additives contribution. Kerosene and Barsol, on the other hand, were in this case. So as far as additives were concerned, any dilution seemed to mitigate those effects. We did this with some other products. So Mobile SHC, synthetic hydrocarbon 320, is a PAO-based oil. So this is the PAO I was mentioning earlier that has low solvency. And what we noticed was that there was a considerable effect from the base oil in addition to the anti-foaming additive In fact, even our standard 1-to-1 dilution was not masking that product. And obviously it has to do with the low solvency of the base oil itself. So that was quite interesting for us. So, it's even shown us here that we're probably going to modify our method to go a 1-to-3 dilution, because at 1-to-3, or 2 parts solvent, 1 part oil, we were getting the counts that we wanted to get. So, yeah, it seems in this case with PAO oils, you need to go to a 2-to-1 dilution before you get the appropriate counts. And we showed that out with we just purchased an Irving synthetic compressor oil, and it turns out that that is also manufactured with a PAO. We got the MSDS, and also has quite a higher treat of silicone oil to produce or prevent anti-foaming. And you can see that some of these stuff like butyl glycol ether, for instance, was actually causing a worse problem than the undiluted sample. Our standard toluene IPA mix, though, was bringing those counts down. Same with Dowanol. Even a small amount of Dowanol and kerosene was also effective at reducing that. Anyway, so what's the bottom line? Well, the bottom line is, this is an example that we did with a particular wind farm, 133 wind turbines. They sent us 133 samples at a time. We do the particle counts with a toluene IPA as a solvent. We get those low counts. That costs that company no money in maintenance. We did it with kerosene. That spec is above the OEMs. They would have had to go and change the filters in every one of those wind turbines. Just the filters, not change the oil, just change the filters. At $700 a tower times 133, it was a $93,000 maintenance bill to do that. So, I mean, it's a dramatic example, but it's showing that even what the laboratory is doing in here, which solvent selection using for this particular method that's supposed to solve our issues with particle counting globally, there's a dramatic effect there.
Bring them into the plants. You set them right, set your filter that goes off, and they'd set a target at, say, 16, 14. They run it on that machine. Call us back. Right for 5 days of filter, because I can't break it. Stop, it won't get. Done the sample in. We were down to 14, 10, 9. So you got all mad, bent out of shape. That's going to take us time. That's the kind of stuff you run into out there too. So it has a lot to do with that costing, right? They just figured that they had overspent getting the right bill of tools, demanded their money back, and we run them in, did the testing. All we did was help them recalibrate and say, look, things are running. If you know the particle count, you beat it up, it's 21, 19. So run it for 8 hours and you drop to 17, 14. Odds are you're going to, if I do the test at the lab, I'm going to be now 15, 10 ninths in that range. So you just got to scale yourself a little bit, because one ain't the same as the other. We find it with
Yeah, sure.
So I was just telling the guys in terms of what Bill's showing with these lower particle counts based on the costing and stuff. And I had a lot of customers that put these offline particle counters on their filter carts, and you're able to set them at a certain ISO code, and they'll shut the cart down when they achieve that number. And a particular customer had about 5 of these units running, and he couldn't break the target that he had set into that machine. So he was quite upset that these things cost him so much money, and they weren't helping him in the field. But when we did the oil samples with the diluted system, his numbers were like 17, 16, 12, let's say. and he was shooting for 16, 14 10s, couldn't make it. But when we did the testing at the lab, they were down like 14 9, 14 10 9s. So we knew that the systems were working, the filter systems were working. It's just the on-site particle count did not maintain it, couldn't get it to work in a good time faction. So they were running them for 6-7 days. When they did the sample after 1 day, we had hit the 14, 14, 12, 10. But they were running them for 6 more days to try and get that particle to shut the machine off, and it wouldn't do it. So they demanded their money back. So we had to do some real navigating with them to help them really co-manage the offline cart with the testing inline, and then they became a lot more comfortable with their readings on the particle counters. It just goes to show when you invest these monies into these machines, it's not all black and white. You really got to know what you're looking at and then try to come up with the solution.
Yeah, so the problem there is that they've got a lot of insoluble in those oils. They use them for a long time. They don't change it out. They just get the dirt out. So there's a problem there with that as well. But unfortunately, yeah, they're spending a lot of money on filter changes on those carts, and that's not really the effect you want to have. So this was another study that Sonia did, and this is something that's always been a suspicion. We talked about this with very low levels of micron filtration. Is it possible to remove some of the additives? And I used to always balk at that. But I think, if anything, the things like the anti-foaming agent, it's possible because it is a fairly large molecule. So this was a study done, and I will caution this because this is done in a lab using lab filtration, basically meaning we're using a patch and we're passing oil through it and then we're doing a particle count. So it's not like doing filtration in situ. I think it's definitely a study we should do. But what Sonia was able to show that, so this particular customer with this ATF product was getting fed up that it was always showing up dirty with their online particle counter because they weren't using dilution and it was additives, that they started employing heavier duty filtration at the plant site to try and filter the oil up. So they were using 3 micron absolute filters, and then that wasn't doing what they wanted. So they went down to 1 micron absolute filtration. So she reproduced this in the laboratory and was showing that the ppm levels from elemental analysis of silicone, which would be an indication of anti-foam in the oil, was actually going down with this filtration. She also noticed that calcium, which is part of the calcium sulfonate package or the detergent that's in there, was also going down. So they were stripping out some additive. Does this happen in standard filtration out there? I'm not quite sure. I think the pressures in filtration industry are a lot higher, and I think that basically the media is a lot different than what you're doing in a laboratory. And you're probably, what's happening in those molecules is they'll tend to line up and go through the filter. And I think in this lab environment, it's kind of a test with a low sort of vacuum and hitting a 1 micron thin layer patch is you're going to trap them for sure. That's what they're designed to do. So we do in the lab because we want to gravimetric measurement and we want to do some actual microscopic measurement. But I think this would be a little harder to reproduce in the field, but it does show that there is that potential. The reason I'm bringing this up, though, is that, again, it's because this customer was, instead of getting particle counts that are actually representing the amount of abrasives in the oil, which was their concern. This is brand new oil. We want to put it in our equipment, but we have to meet a certain spec before we can release it. So they're going through all these crazy upgrades in their filtration system to a point where they're potentially stripping some of the additive out there. And now they're going to have more issues with their equipment because it was based on these phantom ghost particles. So just to sum up, what did we learn? We learned that water and soft particles do have a dramatic impact on the ISO cleanliness level of oils when we do testing, whether we're doing it inline or doing it on site or doing it through a laboratory. Dilution method for particle counting has had a really dramatic improvement. It's also allowed us to do high levels of automation for particle counting, so we can do more particle count tests quicker and less expensively. So it's now part of most people's oil analysis programs, which is a good thing. But the problem is that some of those solvents that are being used as a diluent in that method are not effective. We certainly know that a number of them have no masking capability for water, and that some of them are not effective for soft particles or additives as well. Ultrafine filtration, there is a potential for the removal of oil additives, and generally if it's about achieving oil cleanliness levels, we want to make sure that before we take any dramatic action, we want to check in with our laboratory to see how they're doing this testing. And we want to have a little bit more knowledge now to go back to them and say, are the ISO cleanliness codes I'm getting on my reports actually representative of what I'm seeing in the oil? Questions? Yeah. Mhm. So particle counting is only one test that's done for a standard oil test or an oil analysis program. And the point of this is that particle counting has always been developed and used in laboratories and on site for the specific purpose of measuring the amount of abrasive particles in oil. That's what's out there. It was developed by the Fluid Power Association that comes out of the hydraulics world, and they know that solid particulate is the leading cause of machine failure in hydraulics. 85% of failures because of abrasive particles. Yeah. So yeah, it's a cycle aware. So when you have high particle counts and actual abrasive particles in systems, and then you start improving filtration, it takes time for that system to reach a new equilibrium. And you go through lots of filter changes until you get there. Once you achieve low levels of cleanliness, if you keep everything in control, it's easy to do that and maintain it. Less filter changes, actually, and less wear, especially in the pump. Pump reduces a lot of wear, and the pump also has a lot of wear as due to abrasive. We have other tests that can measure insolubles. So the insolubles that we're masking, we measure using the MPC tests. Membrane patch colorimetry or ultracentrifugation is another method that we can quantitate the amount of those varnish particles, because they're not important in all systems. They're important in systems that have valves, spools, solenoids, but they're not important in gearboxes. You want to have varnish in your gearbox? It's not going to cause a problem, right? So we want to separate those values. Same with water. We do Carl Fisher analysis. We do a colorimetric measurement of water. We get an exact precise amount. We can measure, is it going up? It's going down over time. So we can measure these other properties that are in that oil without having to kind of sacrifice the particle count for that. So we want to be able to distinguish between water that's causing a problem, varnish that's causing a problem, and abrasive particulate that's causing a problem. Yes. So one of the nice things, though, is that in the past, this wasn't the case. Before the dilution method, we've been doing particle count for decades, 40, 50 years before that. And I remember we did a study with a manufacturer here in Oakville, and they were constantly having their oil filtered and putting it back in their hydraulic machines and having lots of failures, and they couldn't understand why. You take the oil out, it's hazy. At the time, we didn't even know what varnish was. It wasn't, that's 30 years ago. People didn't know what varnish was. But one thing we started to realize through industry education was that insolubles and varnish was playing a big factor in systems like turbines and hydraulic systems and circulating oil systems. So we were trying to say, well, could we look at oil color? Could we look at viscosity change? Could we look at the particle count to try and see if there's any varnish in there? And the truth was we couldn't correlate that at all. But with yeah, sorry. The question was, what was the question again? Oh, yeah, yeah. So in terms of, we're removing the soft particles, we're removing the water from the oil by using a solvent. So now we're not measuring that. So we're not, being alerted to that, but the case is we're doing other tests for that. But what's interesting about the particle count is if we just do a standard 1-to-1 dilution, and I look at a particle count result and it's extremely high in 4-6 micron compared to the other sizes, right away I suspect varnish. There's probably so much that just doing that 1-to-1 dilution is not enough. So in that case, we'll do up the dilution ratio. And if the numbers drop significantly, it shows that there's insolubles. And then I usually recommend somebody do an insoluble test because it costs a bit more than standard. Once they do that, then we can definitively tell them if it's the insolubles in the oil that are causing the issue. And again, that's only where it's important in those systems. Not all systems is it an issue.
I have a couple of questions here. I want to mention something regarding filtration, and that's based on my experience in mining.
Can they hear you?
Hear me there? I just want to comment something for the people in the room and some of the people that are calling in regarding removing anti-foam. So this is based on, and there is actually a co-engineer at the time now, an engineer that used to work with me at Arekari Diamond Mine. So we started using CJC Jensen filtration units for big differentials on the 793s. 793s went from, there was a recommendation from CAT to start using the FD1 a new to replace the TO4s. So it seems that FD1 new standard oil was having a lot of anti-foam. So what happened is that in the mining business, sometimes you get the unit in the shop and they connect the filtration system, 3 microns absolute, and sometimes they can be filtered for 8 hours. For how long is that unit there? It's going to be that filtration system working. It's 1,000 liters around that for the 793s, differential and finals. And we noticed that at certain point, everything on the oil analysis was showing all right, no problem. But we got called from the mechanics that the oil looks like a Guinness beer. And you couldn't find out what was happening because the oil analysis was showing no problem. And it seems that it was either a combination of removing that particular anti-foam. Now, we couldn't go out there and all of a sudden replace 1,000 liters for multiplied by 7 trucks at the time. So we had to actually call and make sure that they could take some of the volume, like say 10%, 100 liters, 200 liters, and put new oil in there to refresh the anti-foam, because it was actually a very stable foam, like a Guinness beer. We never did a full study like Sonia did or you are doing here, but we are absolutely sure that that was removing the anti-foam at 3 microns, just because it was repeated for 8 hours at the time, right? So just to mention that. I'll go back to some. Okay. So,
of filtration is 6 ppm silicon typical for motor oil. You want to go back to that slide? Or?
Yeah, sure. So Ken's asking about typical silicone levels in oils. So here I mean, when we're measuring elemental analysis, we're not specifically looking at additives, but if we know that there's certain additives in oil, we know that there's organometallics involved. Sulfur is usually part of the base oil package, can be part of the antiwear. Phosphorus is usually a bit of the antiwear. It can be zinc diethiophosphate. Calcium's like calcium sulfonate's part of detergent C. Silicone, though, is a little trickier because there's so many sources. Manufacturing greases from actual seals. It's part of steel, right? You're going to see it in ceramic. It's showing up from all different sources. Dirt in the environment, aluminum silicate. It's also the only thing we're going to see from the silicone oil or this anti-foaming additive that's present in there. And in this oil, that's a high treat rate. So when you see a native value of 6.7 of silicone. So we know in the new oil, it shouldn't be dirt or any of these other things. We can assume that's anti-foaming. But in an engine oil, it would be much lower. I think it would be around 2, 3 at the most. So that's a big problem with it, is that the silicone level is usually so low. It's kind of at our threshold of where the detection limit is in used oil analysis, that it's very hard to say anything definitive about removing anti-foaming agent. And the minute it's in use, then all bets are off because the silicone sources are numerous, and it's likely not the anti-foam package we're looking at. So I hope that answers Ken's question.
So the other question, why it says what equivalent to test for oil?
So the question is, why is it more prevalent to do oil cleanliness tests on new oil? Because we're putting them into machinery. So I think the kind of the myth out there is that, and this happens so much. We do a lot of off-road construction warranty programs. So Caterpillar, they kind of started used oil analysis. Really, they made it commercial by doing oil analysis on all their used equipment to sell parts. I mean, it's part of their service program. So Komatsu and Liebherr and Volvo and Hitachi, everybody followed suit. John Deere, and they all have extensive warranty programs. But I know when I'm diagnosing samples and I'm looking at the particle count in one of those hydraulic excavators, and it's over what the OEM specifies as their target. Maybe it's 1 or 2 codes over, and I'm telling them there's a problem. What are they going to do? What's the first thing they're going to do? Machine's under warranty? I'm going to change the oil, right? So it's probably sitting in a field. They may go do service, send a truck out, pull a hose across a dirty, muddy field, hook this thing up, drain the oil out, put in new oil. So now we've drained the oil out, where all the dust and dirt from that environment just went in to replace the oil they drained out. Now they fill it full of new oil, which may not be clean as we think it is. It's probably dirtier going into that machine in that environment than it was in there. You use these expensive Liebherr or Komatsu or Caterpillar filters to clean it up to the point where it was. You probably got something else going on. Maybe it's the wiper rings, or maybe there's a leak in the cylinder. It's got some abrasive wear. So this is why it's unfortunate that a lot of time people aren't taking the right action based on the ISO cleanliness codes. But one of the issues is certainly new oil. And we want to make sure that new oil going into equipment is cleaner than the oil that's in there, so that it's much cheaper to clean oil in storage than it is at the machine. So the closer we get to the machine, the more costly it is to be doing that cleaning of the oil. So usually when we put it into a fancy hydraulic system and it's got some big pressure filter drop-in type filters, I mean, this might be $1,000 a pop, right? Meanwhile, I can have a simple oil storage system over here. I can run some spin-on high beta ratio filters, and I can let that oil sit there and cycle for 8 hours inside that tank and get that oil to a very, very low cleanliness code. And then if I'm transferring that into the equipment using the proper, or into the machinery itself using the proper hardware, I can keep it that clean. So now it's effective doing an oil change. If you're changing oil and the first thing you do after you change oil is change filters repeatedly for the next 2 weeks, there's probably something problem with your storage and handling, and you should be doing particle counts on your new oil.
So the next one is common. It says very informative. What are you in action? The cheapest.
Oh, thanks, Ken. I think that was a plug. Don't use the cheapest lab. Use the right lab. No, I mean, I agree with you. Where's the hard ones? Ken is the guy like on a Friday who sends me an email, and it's the most obscure ONS question I've ever seen. And I'm like, there you go. I've never been asked that before, Ken. And I had to think about that one for a while. But no, Ken has a lot of industry knowledge. And usually when he comes, it's something very obscure I've never heard before. Seems like he's just throwing me softballs right now. I appreciate it.
So I think questions about this slide. He says, is this analysis for new oil or used oil?
This is new. And so that's why we can make some type of conclusions about the fact that additives are being removed, because if this was oils in use, then we couldn't. Even amount of, you get water mixed in with the oil, you can have added a precipitate and dropout. One of the problems with oil analysis is that even though we do the elemental analysis, and that ICP that you saw out there, we do over 30 elements when we do an oil sample. So it's a lot of data. And if it's a new oil and we see calcium and phosphorus and zinc and elements like that, we know it's part of the additive package. But when the oil gets used, those numbers don't go down. It doesn't disappear. The additive becomes denatured or gets used up, but the elements still remain in there. So we can't tell anything about the quality of that additive by just looking at those elements. There's very rare circumstances where they do vanish or disappear from the oil. So in this case, because this is new oil and we're doing just filtration on it in a lab environment and we're seeing those elements disappear, we can make a conclusion that we're removing that additive.
Okay. Can is easy to keep them out than to provide.
Oh, there you go.
One says that exactly should
Anything. Who's going to win the Stanley Cup? No.
But I have a question.
Please.
Sometimes I have heard this funny, I think the gearbox is foaming with the oil. Just a couple of puff of the silicone spray and the foaming there.
Well, a lot of treats for any of them. So you talked about methacrylates, but you know, a lot of these polysiloxanes are silicone-based oil, and that's what the treat is. So I do know that one of my colleagues is George Shinuski. He's done a lot of work with reliability with Ontario Power Generation Nuclear. He's now retired and consultant, but still talk a lot. And I know that he developed a program for steam turbine oils there, because we're talking 30,000 liter reservoirs at Pickering and 60,000 liter oil reservoirs over at Darlington. And when that oil got aged and used for 5, 6, 10 years, what starts to go is these base oil properties. So water, you saw some of these tests in here. Water separability is one of the first things to go. If you do have a gland leak or you have a cooler leak, the water is going to is not going to separate readily from the oil and be able to be drained off in the reservoir. Foaming goes. You start to see foaming occurring on the oil itself. So what they were doing is they were actually doing foam treat. So he would be remixing in some of these silicone oil to try and treat it. The problem with that is it was throwing other properties off. So it was a great try. It mitigated the foaming problems, but it was introducing problems with water separability. So the water separability would be thrown off dramatically by doing an overtreat with the anti-foaming agent. So yeah, foaming is one of the things that goes when the oil gets very degraded. Now, I don't know what the application is. We used to have this engineer come in from a local cement plant, and he would constantly be complaining about his oil provider saying, my crusher gearbox is constantly foaming. It's the oil. And I'd say, you're a cement plant. It's cement dust. Like, you have felt seals on it. Cement dust causes foaming. No. It's the oil should handle that. And it's like, well, it's well known that cement dust causes foaming. So certain additives do cause problems with the oil. So it depends on the application. In a gearbox, usually you see foaming because it's an expensive gearbox. It's in a tight little space. It doesn't have much of a lubricant reservoir. So there's a lot of agitation of the oil in that thing. It's high speed, and there's just not enough oil volume. So you need to actually find a specialized oil that has a higher anti-foam treat rate for that, or a synthetic fluid or something.
Over here. So my question is, well, since we are seeing a lot of misinterpretation and users in different fields, do you think it would be good to have like a procedure to actually validate their numbers with their online particle counts versus what you can get here on the lab by using some of those dilution that you've already been doing? Because we keep on seeing this a lot. It's not only manufacturing, it's not only wind turbines, it's some of the mines that they want to have the 5 stars or the 4 stars as per cut. They want to make sure that their oil is quite clean compared to even cut standards. And sometimes they miss this particular, how you're taking the sample, all that kind of thing. Do you think that that might be a good idea to have like a procedure to say, okay, if you get 2 counts on a calibrated machine, but it's not doing dilution, that means that that means that probably going to be, if we do the same thing at the lab, going to be 3 counts less or 2 counts less or something like that. Might be something that we can utilize for several other customers.
Yeah, that'd be a good article to write there. How do you validate your own data, either from your own lab or from your own on-site? I've kind of been lucky in the last year or so to actually audit some on-site labs. We did OPG's nuclear labs at the 2 nuclear power stations. We were involved in the CANDU owners group where all the lab people came and talked about it. And we were looking at some of the methods they're using in nuclear power plants to monitor the oils for the accessory equipment, for the steam turbine oils, and especially for the fire resistant fluids, right? So the real lubes and the Farquals and these products. And the truth is, even their own in-house labs, they're not following methods properly, or they're not using the right method. And then they're doing maintenance activities based on a single number, looking at an acid number and changing out 20 barrels of oil. And it's like, you might want to validate that number. Well, we use this method, it's very repeatable. Yeah, but the way you're doing it is not repeatable at all. So yeah, it's a tough one. I don't just say it because I've been in the industry, but oil analysis is tricky. It is very tricky. That's why there's so many training courses. Everybody does training now. There's so many courses out there. There's not just the Norias, there's the Wurzbachs, there's the Amris, it's just allied. Everyone's doing training, and everyone on all these different levels of certification for this. But it's a complicated field, and I was just having a discussion. We had a quality meeting today in our own lab, and I was talking how about, as an analyst, you need to understand your own laboratory, because you need to know what problems can occur with your instruments. You need to know the quality of your instruments and whether you can trust the results coming off. And when you don't trust the result, why? And even to the point where even lab techs, what lab tech was running that today? How trained are they? Even I can't make a decision on a number until I'm confident with the number coming out of the lab, because I know that has a real world repercussion and could cost an extraordinary amount of money to the customer. So yeah, I think everyone should take those values with a grain of salt and find another way to sort of validate. Even, these nuclear power plants, I'm trying to steal stuff from them and put it on my coat and take it out because they don't use it. But there's no money can't be spent at these places. Budget's not a problem. It's about increasing equipment life in them, and it makes sense. There's a microscope sitting under cover. It's worth 30 grand. I know that. It's a beautiful axial Olympus. Can I have it? You're not using it. You should be using it. There's a little kit there. You take a pump, you put it through a filter patch, you put it on their microscope. You got unbelievable $15,000 Olympus software to go analyze the particles. If you don't trust the particle counting you're doing on site, take a patch, throw it on that microscope, and validate. Are you seeing those high counts or not? So there is ways you could do it. If you get a very high particle count, it doesn't make sense because you've been running your cart for 3 days on this, and I got a Donaldson beta 2003 micron times 2. Just take a sample and hold it up to the light. Can you see through it? No. Well, guess what? It's full of varnish. You'll never get the countdown on that. Yeah. And it's not all bad news. At the one nuclear lab, they do that. They have all these screening tools that are part of the program. The color, they do ASTM color, they do clarity, they do debris, and those are really good practices, because sometimes that's the most important thing you're seeing in an oil, and trending that in that system is more critical than a lot of the other tests you can do. Yeah.
So, 2 comments. One can say that the oil suppliers should
That's a good idea, because there's a lot more scrutiny on some of the other tests. I know with MPC, I just was commenting on LinkedIn recently with one of my colleagues, and when you produce that MPC number today, you're supposed to produce another number, and that was the question. What's that number? And it's the incubation period. So labs are supposed to be incubating those samples. They're supposed to reheat it for 24 hours and then incubate it for 72 hours before doing the MPC test. And so is that being reported by your lab? If not, you need to question the results. So I love that idea of saying, what's solvent? And further to that, at the back of the room is my colleague Alistair Geach, and he produced a lot of the data that was in this paper. And I encouraged him, and he is now part of the ASTM 7647 committee, has been for a few years, and he's getting all the nice warm frustration that all ASTM goes through when you try to reapprove methods and go through ballots. But the point is that we're bringing this data forward to the ASTM in order to say, look, we've got to take some of these solvents out of here. We've got to add some addendums to this method, because what ends up happening, it's not like a laboratory says, we want to do this wrong. But a lot of times it's, say, an oil company, they're highly regulated. when they look at toluene, they say, well, that's a hazard class of a 3, and Dowanol is a hazard class of a 1. Use Dowanol, or use kerosene because it's a hazard class of 0. So as long as it's in the method, then they can do that, because environmental group's going to go use this one. So really, it comes down. ASTM is one of them. So I'm talking directly to Ken right now. So I think this has to start with Ken. I don't know if it's going to start the oil companies. Start with Ken. It has to start at the ASTM. It has to start with Alistair, people like him. So we have to make sure that the methods are backed up and supported by real scientific data, so that laboratories are aware. Because even, sometimes I sit down and read an ASTM method for the first time and go, oh, I've been doing this for 33 years. They put you to sleep. I'm sorry. There's a lot of them. But if you're actually looking through the method, though, and this is saying, nope, this is good, then how are you going to disagree with that? So starts with ASTM. Yeah, that's great. Perfect. Yeah. Yeah, so
Thank you very much, Bill. Novia, for the whole web check. Thank you, the Hamilton section. I don't know how many people besides Bill Ridley from Hamilton, Toronto, not quite a bit of them, but hopefully we can contributing, cooperating with the Toronto and the Hamilton section. We did that the 3 days course. We were part of that too. So that was shared to our Toronto. We're gonna send more info about what's gonna happen next, but I think it's gonna be the last of the year because